All right, so my video just randomly stopped in the middle. I'm not sure if it's because I'm doing it from home or what, but it's annoying. But anyway, we'll finish this up and we'll be fine. All right, so erase, if you didn't get a chance, erase, well, not, you don't have to erase, but maybe use a different pencil or erase it if you want to. It's up to you. I erased it. And for the second one, we want to approximate the integral from 0 to 9 of f of x. So that means I want a vertical line at 0 and one at 9. And I'm going to figure out which approximation method whoever did this was using. All right, so we start off with 5 times 3. So that's some kind of base times height or height times base. So that's what we have to figure out. And so the 5, I would think, is that 5 right there. And the 3 should be this base distance, which it is. So I would draw a rectangle that has a height of 5 and a base or width of 3. Okay, there's that one. And don't forget that in this problem, they're using the dark endpoints on the curve. So that kind of helps a little bit. So for the next one, I have this 2, which should be that 2 times 1, which should be this width right here, and it is. So I would draw that rectangle with a height of 2 and a base of 1 unit. All right, so let's keep going. We have 3 times 2, so the 3 should be that height right there. And then the 2 should be this width, 2 units. So that's the rectangle I would draw with a height of 3 and a width of 2 units. Okay, and then one more to go. We have 6 times 3, so 6 should be that height, and it is. 3 should be how wide this last rectangle is going to be, 3 units wide. My rectangles are kind of jacked up, but that's okay. Okay, so then when I go back and I look at what the rectangles that we drew, the left point of each rectangle is sitting on the curve. So that should be a left Riemann sum. And again, we talked about it with the trapezoids a little bit. You don't have to have equal widths when you do Riemann sums or any kind of approximation methods. All right, we have another scenario. So scenario 2, the table below gives the velocity values measured in feet per second every 3 seconds. And so I have this definite integral from 0 to 6 of the absolute value of the velocity of t dt. So we need to figure out what method we're using this table. And so we have 10 times 3 to begin with. So the 10 is going to come from this 10. And then that would mean the 3 should be the width of the rectangle. So if I look at from 0 to 3, that is a width of 3. Okay, and then for the next one, this one is a little different because I have 15 here, but I have negative 15 there. Where do you guys think that came from? Like, why did it change? Well, the reason it changed is because our function is the absolute value of v of t. So that's why we use the 15 and not the negative 15. All right, and then the 3 should come from the width between 3 and 6, because we are going to 6 on this one, which is 3. Okay, so then we need to look and see, do we use the left or do we use the right part of the absolute value of the velocity? And so on both of these, that is the left. And then on the second part, we're not using the table on the second one because it's a totally different function. It's f of x, not v of t. So it's some random function. We don't know what it is, but we're finding the integral from 0 to 6. So I'm just gonna draw a random function. Okay, and we're gonna go from 0 to 6. All right, so the first part, we have f of 0. So that should represent the height. So f of 0 would be this point right here, the value of the function when x is 0. And then 2 should be the width. So I would put, it was changing by 2. So 0 changed by 2 would be a 2. Okay, so that rectangle should have a height of f of 0 and then a width of 2. So that right there. All right, the second part, we have f of 2. All right, so that should be the value of the function when x is 2, so that point right there. And then we're multiplying that by 2, so that would have another width of 2. I didn't draw this perfectly, sorry. So 2 plus 2 more would be 4. All right, so we want a rectangle that has a height at that green point and a width that's 2 units long. All right, and then finally, we have f of 4, which should be the point of the function, the value of the function when x is 4, and then a width of 2 again. So that would be that height, and then 4 to 6 gives you 2 units. Great. And as we look at that graph, it also is a left Riemann sum because the left point is on the curve. All right, so some of these you do kind of have to get creative and draw your own graph and just kind of go through what the approximation is saying. All right, so we're going to fill in the blank with the method that is described. So for any subinterval, a blank involves adding areas of rectangles where the height is the y value on the left side of the interval, which is multiplied by the width, which is the change in x values of that interval. So that should be the left Riemann sum. All right, and then a blank involves adding the areas of rectangles where the height is the y value on the right side of the interval, which is multiplied by the width of that interval. So that's going to be a right Riemann sum. Okay, we have a little bit more to do. So this, we're going to be figuring out greater than or less than the definite integral. So remember that on an increasing function, a left Riemann sum underestimates the definite integral, and a right Riemann sum overestimates the definite integral. Right? On a decreasing function, it's just the opposite. A left Riemann sum overestimates, and then the right under. Okay, and then for trapezoidal, you look at the concavity. So if a function is concave down, a trapezoidal sum will underestimate. Concave down is underestimate, and then for concave up, trapezoidal sum will overestimate. All right, so for each of the graphs below, we're going to determine whether column A or column B would be the greater value, and then we're going to explain why in the final column. And if it's not stated, we're going to assume equal number of subintervals. Okay, so for the first graph, we have it drawn. It looks like it's increasing and concave down. So let's think about what would happen on a right Riemann sum. So I'm just going to draw a little one because I think that will help you on this when you're doing it on your own, where you don't have these bullets above that tell you what to remember, that you may have to depend on drawing. So the right Riemann sum, the right point, the right corner of the rectangle is touching the curve, and you can see that that is going to be an overestimate. All right, so let's look at what happens with a trapezoidal. So I'm going to draw a wide trapezoidal, because sometimes you have to be able to see it on the trapezoidal. So there's a trapezoid, and you can tell on that trapezoid that it's going to underestimate because there's a part of the area that's not covered. Okay, so then an overestimate is always going to be larger than an underestimate. So the answer is that column A is greater, since a right Riemann sum estimates a definite integral on an increasing function, and a trapezoidal sum underestimates on a concave down function. Okay, so that's what we're going to do for the next one. Some of them are going to be more difficult, so I'll keep doing these with you. All right, so let's look at the next one. So F is decreasing and F is concave down. So a right Riemann sum, I can just draw one rectangle with the right corner on there. That's going to be under, because there's area that's not covered in between this area right there. All right, and then we have the definite integral from A to B of f of x. So that is going to be exact. All right, so then we have to figure out which is greater, an underestimate or an exact estimate, or an exact value, not an estimate, an exact value. So column B should be greater. Because a right Riemann sum underestimates on decreasing functions. So let's look at the next graph. F is increasing and concave up. So we want first column A, a trapezoidal sum with 3 equal subintervals. So let's just go ahead and draw a really wide trapezoidal sum. And we can see that it's going to be over. Okay, the next one is a little tricky. So we also have a trapezoidal sum, but this time with 6 equal subintervals. So it's still going to be over. However, it's the more subintervals that you have, or the more trapezoids or rectangles that you have, the closer the estimate is going to be. So it's going to be over, but it's going to be closer to the actual area. All right, so then think, which one is going to be greater? They're both over, but one of them is over by more, which is going to make it larger. And that's going to be column A. couple more. So F is decreasing and concave up. Okay, so let's think about trapezoidal sum. All right, so trapezoidal sum is going to be over. Okay, and then a left Riemann sum. So the left point is on the curve. All right, and so it's also going to be over. So then we need to think about which one is actually closer to the value of the actual area, and that's going to be the trapezoid. So trapezoid's over, but closer to the actual area. All right, and then we're kind of in the same situation we were before. They're both over, but the left Riemann sum is over by more. So column B is greater because it is over by more. All right, so you could try this last one on your own. Okay, so we're kind of in that same situation. They're both over. The more subintervals means that column B is over, but closer to the actual area, which is going to make column A greater. Because it is over by more. Okay, so what I want you guys to do on your own is the rest of the packet. And so we have a check for understanding here, where you are matching graph with the correct description below. Right, then you have another, it's kind of like what we did, but in reverse. And so you have the method that you're going to do it by left Riemann sums. You're going to use the actual points that you're given and find an approximation for that definite integral. So you are writing out what this stuff right here on those. Just kind of reverse what we did together. And same thing on that. And that's it.